20 minutes. Okay.
Yeah. Actually, I'm quite glad that we're the only team for today, and just whatever the reason is, just I feel really glad. And actually, our work is on a text hierarchical classification with the feature selection, and we use our methodologies into the application in China's group buying data.
Can you explain what group buying data is?
It's just similar to eBay. It's a kind of China version of eBay.
Oh, the group buying is a website.
Yeah, it's kind of a website.
All right. Oh, it's like group.
Oh yeah, it's
Okay.
like group. It's not like it's like group.
Yeah.
And basically, I'll firstly introduce some of the motivations and challenges about the text hierarchical classifications, and maybe some of the points that could be related to the group buying data. Firstly, the text hierarchical characterization or classification is basically it assigns pre-trained categories to online text documents, and which is pretty effective way to do if you want to do information retrieval from the online manner from the websites. And actually, it's kind of glad that there are already several methods that have been developed in this context, and we would like to study this method and maybe do something from our own standpoint. And basically, in this context, the basic challenges are the biggest challenge are the imbalance in data sets. It's because for some of because normally the text mining, for each of the text we have a very large feature sets, and for each of the documents maybe we have only a few words, and so that if you want to train a classifier for that set, the imbalance between a different a 1 and a positive 1 and minus 1 would be really imbalanced. And the second point would be the high dimensional data, because it's not really high dimensional because P and N and P are in a kind of same level, but there are still a lot of challenges caused by this fact.
What is P and N?
P is the P feature dimensional. It's the number of dimensions, and N is basically the number of observations. It's kind of related to the cursive dimensionality. And the outline also of our work is basically we want to do a comparative study on the different methods on our data set, because we have a data set about the China's group buying. And also, we propose our own L1 penalized embedded feature section to obtain a robust classifier, and we do a comparison of our method to kind of all the current methods. And firstly, I'll introduce some data descriptions. So our data come from the group buying websites in China, and basically we have 3 websites. Just like I mentioned before, they're just very similar to Groupon. It's kind of China's version of Groupon. And the time span of our data is basically from March 2010 to December 2011, which varies between different cities. Yeah, we have a city scale from a very big city to small towns. We have 32 cities in all, and also we have in all we have more than 30,000 observations, and also a comparable feature size. And categories are basically we have 56 categories in all, and we have 3 levels. And basically, there are more categories in the down levels.
Can you explain what one observation is in this data set?
What? Pardon?
Can you explain more about the data set? What is one observation like? What data contains?
Oh, I see. Basically just as here it says, basically each data contains each of the transaction on a website. Basically, it describes the
The product?
Yeah, it's kind of a
Okay.
description for the product on the website.
Mhm.
And also, maybe we have actually more data about that. For each of the products, we have like the number of people like participating in the group buying, and also the time, and also the.
What the category is about?
You mean
The categories?
Oh yeah, the categories are actually, because we are doing like text hierarchical classification. We have the description for each product, and we split the description into a feature set, which basically mean into a dictionary, and to see whether the words in the documents are like marked by the dictionary.
So are you classifying the products, the transactions, or?
We're trying to classify the product.
Okay.
So we have the description for the product,
Mhm.
and we just map it into a dictionary.
So what's the difference between samples and observations in your case? I'm a bit confused.
Because samples are like but I think they're basically the same.
Okay, so
It's the same.
but they are very different numbers. So
Oh yeah, it's like
That's each city.
it's
Okay.
for each city.
okay,
Yeah, we have like a
and then you just aggregate everything.
yeah, just add up everything we have. In all, we have like.
And is there a
30,000.
significant covariance shift between the cities?
Yeah, there should be, because
Yeah.
there are large cities and also there are
Yeah.
small towns.
Mm.
Yeah, and they should be very different.
The features in this case, are they just words, like it's a dictionary of words?
Yeah, it's a dictionary of words.
Okay.
And the text classification is very useful for managing the website, and also it can help to like provide insights for market analysis. It's very interesting for that's kind of another like, course project for another course.
Which course is that?
It's the applied
250B.
statistics. The 250B.
Applied statistics.
Right. That's,
Okay.
that's for like market analysis. And basically, I'll introduce some of the methodologies. And we have 3 points. And the first is the hierarchical classifier we use in our work. And the first one is basically K-nearest neighbor is kind of a straightforward way to do like hierarchical classifiers because it's basically non-parametric and it's kind of from the standpoint of interpretability, it's kind of straightforward. But the problem is it's very computationally very costly because you have to calculate a very large distance matrix, and it's kind of not a very efficient way.
So do you actually need to do that? Because I mean, you could simply use an inverted index.
Yeah, that's
So
that's
because I
true.
mean, you don't have very many documents. I mean, or you have maybe
It depends on
30,000.
documents.
So a lookup among 30,000 is very, very cheap in an inverted index.
You mean the
So you because you only need to check whether you have other documents which are similar to this.
yeah, that's true.
And there are fast nearest neighbor query algorithms for that.
Yeah, that's true. And actually, for K-nearest neighbors, we kind of during the implementation, we just choose the comparison between like different documents are not by the very complicated distance calculation, just by like map. Yeah, otherwise, it's we just run a simulation in MATLAB. Otherwise, it would be like impossible to run. And also there is another category of methods is the supervector machine. Because supervector machine basically it is very robust for scalability, and but it has some of the interpretability issues because it's just like a black box and you have no ideas about what happens within the context. And the other category is the linear model, because the linear model has the very large advantages. It's very good at interpret the results because you have the access to different features. You can see which feature is more important than others. But the linear models suffered a lot from the curse of dimensionality. So we would like to pursue some statistical method especially for high dimensional data. We have a lasso and one more penalized methods, such as the lasso and one penalized logistic regression, and which will be our focus in our work. And The other part is the classifier structure. Because normally we perform a top-down hierarchical method, which means that firstly we do characterization. We just do characterization for like, higher levels, and for lower levels, when we try to do predictions, we just use all the data from its parent node. So we are not trying to use the whole data set. So that's kind of save time.
So why don't you build an integrated model? So for instance, like the Kai and Hoffman model, where you actually estimate for the entire ontology at once. So remember when we discussed structured estimation? You could do that directly here as well, obtain subgradients, estimate all the parameters simultaneously.
Right, we have also tried that kind of models. For example, actually we have done some work on the hierarchy, like multi-class SVN. There's kind of you train you train at one time a full classifier for all the subsets.
Yeah, but you can build that hierarchically.
Right, that's true.
Okay.
And and I think our problem, if you just simply do a top-down hierarchical classification, the problem would be the results would be not that consistent because you are just classifying each node separately. So you want to do a top-down level, like adaptive correction, to correct the relationship between different nodes to let them be consistent. The other way is to just do bottom-up way, which basically means that you consider the cost, which means actually this method is kind of related to a cost regulation between different layers. It simply means that because you are training during your training of different levels, they have some relationship between each other. If you train, like for example, you train a upper level to be neural, to be like a non, so you would like to all the sun nodes to be not to be all like a neural for that observation. So the cost regulation basically, if you have a parent node to set to zeros, and you will give a lot of cost to the sun nodes, so that you will prefer to train the sun nodes to be all zeros. And for the feature selection part, we have several different. We also try different methods. Because the simplest method is data frequency. Basically, you just calculate the number, the frequency of each item in a dictionary, and you just filter by the words that just almost like you cannot. Yeah, some of the words actually only appears like one or two times, so we just want to filter them out. Actually, after that, we can just shrink our dictionary a lot, because many of documents are only have within 10 different words. So that really helps a lot to reduce dimensionality.
Is that the actual count or the 0, 1 as occurrence?
This is occurrence.
Okay.
Yeah, the count of occurrence.
So why don't you, first of all, if you use lasso anyway, I mean, that's essentially a feature selector.
Alright, that's true.
So why do you have to do feature selection in addition to using lasso?
Because, I mean, for lasso, it is kind of embedded feature selection. But for some other ideas, for example, for SVN,
so do you actually find that the algorithm performs better with feature selection than without?
I think just embedded feature selection, for example, for lasso is better.
No, but what I'm asking for SVM, did you actually find that feature selection improved the results?
Yeah, feature selection somehow just improved the results.
Good. The other question is, so there are attribute rescalings. Essentially, TF-IDF is one of the most common ones. Term frequency, inverse document frequency. Did you use these for the terms, or did you just use occurrence counts?
I think we use both of them.
Yeah, we try the L2 non-scaling and IDF, but the results are almost the same as
Okay.
non-scaling.
Okay.
And also there are another group of feature selection methods which just like you want to calculate the mutual information and the F-score and the chi-score statistics. Actually, the F-score and chi-score statistics are similar because you just want to see the correlation between your certain feature with the response variables. And if the correlation is larger than some values, we just choose them. But those methods has a problem in which it kind of ignores the correlation between different features.
You can try the L0 penalty, like the sparsity stuff.
Yeah,
I'm
we
curious.
can try. I'll introduce them, maybe. Because we tried, you mean the L1 or?
No, L0 no, like, it's 1 if this occurs, if 0 it doesn't occur. I mean, if the coefficient is not 0.
Yeah, but that's rather nasty to optimize over.
Yeah. It's really hard to optimize. I'm just wondering if you.
Yeah, we haven't tried that. Because we just tried we just use the L1 penalized methods. Because that's a kind of embedded method. We can realize in lasso, the way of lasso, or L1 penalized logistic regression, or like L1 penalized SVM. Because they have, actually we got especially for like lasso and like L1 penalized SVM, we have a pretty good like, commercial solution for that.
Can I ask another question? I'm sorry to interrupt. So, to apply the SVM is like supervised learning. Do you have the label of the data? No. Okay.
You mean I mean we definitely have the label data.
You have the label. So
Yeah,
it's
if we
not
really want to
unsupervised.
like do prediction, we have to label the data.
Okay. It's not like it's not clustering.
Right, it's not clusters. It's a supervised. We just want to do prediction, and we want to do testing. And for the evaluation methods, we actually we have different kind of evaluation methods for hierarchical structures. First of all, there's the overall loss, and basically that means for each of the test observations, it is correct. It is correct only when like all the relevant categories are correct. So that's a very that is a very high requirement for testing. And a better choice would be like structural loss. We just consider the results at different nodes as independent, so we just count all the nodes. I'm pretty sure there's a problem.
Yeah, that's
but
just Microsoft not working on a Mac.
Oh,
Sorry.
It's okay. Just it basically means that you just average, you just assume that different nodes are kind of not just kind of independent to each other, so you can just testing them one by one, and you just average the first structures for average loss, or you can calculate the leaf node loss. You just focus on the leaf node, and also.
But wouldn't that be the same as checking the overall loss? Because I mean, I can only get the leaf correct. I mean, there's only a single path to the leaf. Right.
Right.
So therefore, the overall loss and the leaf node loss would be identical.
Yeah, that's true. And I think it's only when sometimes, for example, I choose the parent node to be like 1, and maybe not only one of maybe several of the sub nodes are like they all be 1.
Oh, okay.
That's
So
the problem.
so you can have categories that are not at the leaves.
Right.
Okay. How do you define the leaf node loss in that case?
You mean for the leaf nodes, we just define it to be it has no sub nodes. It's kind of the final nodes.
Uh-huh.
In the categories. We have also, because these 3 methods have some problems, because for our data sets, we have a imbalance between different, for example, for some of the nodes, there are only like very few observations, or just very few observations for certain categories. So it would be pretty good that we just maybe just when we do predictions, we just let them all be like zeros, or that will still provide a very good accuracy, just seemingly very good accuracy. But it's actually a pretty bad classifier. Because that way we just want to create a precision and also precision error and also the recall error. Let me just introduce the precision error. Basically, it is the sum of the.
By the way, you can use the whiteboard.
Oh, I see.
Then you don't have font problems.
Right. The precisions are just sum of the true positive and over the sum of true positive plus the sum of the false positive. So, and also the recalls are actually equals to, there's still the true positive, but the below in the denominator is the true positive and sum of false and negative. So basically we consider the imbalance between the results, because we just give a lot of penalty if we just predict all the observation to be zero. We will give a lot of penalty on the recall parameter, because the false negative would be really high in that case. And we basically we show some of the results here, and it's just a very large table, and we summarized all of the result or methods, and basically you can see that for the overall loss and structural loss, and also the leaf loss, maybe they're quite similar. They're quite close to each other. All the methods are providing pretty good results, and actually for even with the very simple methods, this is the K-nearest neighbor. And also, but for like recall and precision, because this precision 2 is actually, recall 2 are kind of related. We just add a weighted term for like the number of different groups, because they're basically they're in different scales, so that if you want to sum up those true positive where false positive, there might be some problem, because we just do a related sum of the terms. So if you see the precision or recall, the L1 penalized methods would be better than the traditional list. Because for example, for recall, for SVM, and for the bottom, just the normal bottom ups are kind of for using the K-nearest neighbors are not using like a L1 penalized term, so it has an overall like recall for like only 0.5, which is actually pretty bad.
So the one thing I'm a bit confused is, so your leaf loss is considerably higher than your structure loss, right?
Oh, right.
And
Oh,
if I understand you correctly, the leaf loss and the structure loss should actually be the same, except that the leaf loss is a bit less stringent.
The structure laws are kind of like average. That basically means that the father nodes, the parent nodes are maybe have better results compared to the leaf nodes.
Okay, so basically because you might have a hierarchy of depth 5, that's why. Okay.
Yeah.
I see. No, sorry, actually the leaf loss and the overall loss, they should be identical. Sorry, not the structure. Because the overall loss just checks whether you get the label exactly right. The leaf loss checks whether you get the leaf right. So what's going on there? Now I'm really confused.
Just as I have mentioned before,
Because it's a factor of 4, so you have so many inner nodes.
For example, for some of the method, for if you want to do a prediction, for example, you can because you are developing like the classifiers like separately, so that it's very highly possible that many of the leaf, even if they are belongs to the same like parent node, they can all be like ones. They can all be like predicted to be 1. Yeah, that would not be a problem if we just like or that could not be a problem for the leaf node predictions, because we're actually for the leaf node predictions we're actually just after we do a prediction for the leaf node separately, and we just calculate the prediction error for certain for each one of the node. So and for overall loss we are actually like calculating the prediction error for each of the observations, which is calculated even if they are if they are just all right, so we can count them as right. But for leaf node, we're actually training them separately. So that could happen if we use, yeah, we're actually training them. And yeah, and for the recall and precision, the L1 SVM and L1 logistic regression are having a pretty good performance. And I think actually the recall is more it's a better indicator for the robustness of the methods, considering its performance for false negative. And you can see that for the recalls, L1 SVM and L1 logistic regressions are actually much better than just the K-NIRS neighbors. And also there's another problem is the bottom-up classification, as I have mentioned before. It just try to do a cost regulation. It just kind of making the predictions to be consistent during your within the hierarchical structure. So that bottom-up method is not necessarily having a good performance based on our experiments. That could possibly due to the problem during the training, because we're giving because we were thinking that probably we have some overfitting in the training set. And actually the result of the discussion, and I have mentioned something before, because most of the methods are having a pretty good overall loss and structure loss. Yeah. But that might be a bit problematic because of the imbalance in the data set. And L1 which is regression and L1 SVM having a pretty good performance considering the robustness to imbalance. And K-NIRS neighbor has a pretty good precision, but an awful recall, which is kind of related to its nature by it just simply want to find the nearest neighbors. But for the very imbalanced data sets, it's very difficult to find a neighbor. But that's a problem for K-NIRS. And the bottom-up hierarchical method in many cases does not have a pretty good performance. These methods are actually coming from a paper, which is trying to examine whether they have their method is really valuable. But it kind of fails to prove that it's a valuable method. And yeah, I'll introduce summaries because we did a comparative study of different hierarchical classification methods, and we find that L1 method shows a robust performance with a good precision and recall, which basically means that it has a pretty good robustness when you run into a kind of very imbalanced data set. And also at the same time, the L1 and logistic regression and L1 SVM provides a pretty good embedded feature selection, which is we kind of also show some results in the previous slides. For the selected features, you can see that it is not really like because we try to to shrink the feature size into even smaller, but sometimes it's really hard to, especially for text mining purposes, it's very hard to, you want to shrink the data set into very small.
So there's one thing that I'm curious about, because I mean basically for each of those algorithms you have two knobs, right? Well, not for all of them. I mean for some those two knobs are the same, but let's take a simple SVM. And you have one knob which is basically how many features to select, mind you also have to decide which feature selector to use. And then you have the issue of choosing a suitable regularization, right?
Right.
So, how did you pick these parameters in your approach?
For feature selections, because I have mentioned for example, for SVM, we have a pre-processing by like a feature selection. And
Yes, but I mean, you must have some. I mean, those algorithms usually come with at least one parameter, which
oh,
you know.
you mean for example, the panelized parameters?
Yeah, but basically, you know, how many features you're going to select depends on, you know, some quality criterion of some sorts, and those tend to have at least, you know, one tunable parameter.
Yeah, that's true.
And so, how do you adjust that?
We don't have time to do a very like.
Just
Mhm.
use cross-validation.
Very-
So you did cross-validation over the regularization parameters
Right.
and over the feature select. Okay, good.
Yeah, yeah. But
That's what I wanted to check.
Right. Just we did a very like cross validation, but I don't think we have a very like
Hmm?
detailed
No,
analysis.
no, that's okay. But basically, at least
Right.
you had a mechanism to test.
Right. We have a
Hmm.
like, we have a parameter choosing steps,
Good.
and for the oh I see we have some further tasks. That's just for because we can include more like extraneous variables such as the cities and maybe the time of the transactions, and also the feature selection is just kind of yeah, because right now we're just trying to the L1 logistic regression and L1 SVR are just kind of like embedded feature selection methods, and for the for example for the for normal SVM we just do just pre-filtering, just separate pre-filtering, but that's kind of not quite like an integrated way to do that, because we should be able to find other better way to integrate feature selection in our classifier. And that's all.
Thank you very much.